So I want you to think about some of the words that we have used. So let's just think about a quadratic graph. Actually, first of all, let's make it even easier and let's just talk about a linear graph. That is the straightest line I may ever have drawn. Thank you, thank you, thank you. That is amazing. You should be impressed. It won't happen again. All right. So when we are talking about the steepness, obviously we use the word gradient. There is another word or another phrase that we have used that helps to describe what's going on here. Do you remember what it might be? I'm not asking, okay, so the slope, I'm not asking for
Steepness.
Okay, I just used that word. Okay, thank you, Adil. The rate of change. So when we talk about gradients, we're talking about the steepness, which is measuring the change, right? The change in X with respect to Y. So when we're saying, so a linear equation has a stable rate of change, right? As X goes up, Y goes up in the same way all the time. It's consistent. When we get to something like a quadratic, the rate of change is constantly altering, right? It is changing. It is different. We find the gradient here, then we find the gradient here, then we find the gradient over here, right? They're all different. The rate that the line is changing, that the relationship between X and Y are changing is constantly moving around, right? So that is also true for actual problems. So when we were looking at things yesterday, like boxes, volumes of shapes, all of that sort of stuff, we're looking at the rate of change of volume versus length versus, so we looked at a few different options. So the rate of change is the thing that we are really measuring. I've totally lost my train of thought because I can see some people who are not actually listening to me. I really want you just to focus on this because it is a bit of a new thing. So the rate of change is how fast something is changing based on other changing things, all right? Bless you. So let's have a look at how we can, let's just do a really simple version. So I have an equation that H is 1/5 t squared. So what I want to know is I want to find the rate of change of H with respect to T, because that's our equation, when T equals 2. So what I'm trying to do is I'm wondering what the rate of change is at a particular point, because with an equation like this, it's going to be moving around all the time. So rate of change is about the gradient. So what am I going to do? Derive. How do I write the derivative with these two letters? No, I'm sorry. I'm not asking you to derive it. I'm asking how do I write the derivative with these letters? Good. So dh, well, I should have made that small. I don't know why I made that big. dh over dt, right? We are deriving h with respect to t. Okay? No, other way around. We're deriving t with respect to h. Okay, so this we should know is what? Yeah?
T.
Okay, good. It's just 2/5 t. Bring this down and multiply, subtract 1. Now I want to know what the rate of change is when t is 2. So I'm just going to put that in. Why did I write t? That was not helpful. 2, which is 4/5. Okay, so we don't have any units of measurement or anything, so that would just be our answer. Let's now do one when we're actually talking about units, because that's where it tends to get a little more complicated. What's a G? With that? Stop picking on me. All right. So let's do an example where we've got to do a few different things. So what I'm going to do is I'm going to do an example of a point moving along a curved line. All right, so we've got curved graphs, and I would like a point that's going to move around that graph. Jumlin, can you put that away? Thank you. All right, so I'm going to say that y equals x plus 2x plus 3, and that is a square root. So there is a point with coordinates x, y that is going to move along this curve. And I want to know what the rate is. Oh, sorry. The rate of increase. So the rate of increase is constant. And it is 0.06. I would like to know, blah, blah, blah. Yeah, okay, sorry. I want to know the rate of increase of y. So I'm being asked to find the rate of increase of y when x is 3. So the first thing I'm going to do is rewrite this, right? We don't like to use square roots. So how do I rewrite it?
2x plus 3 half to the power of half.
Good, to the power of a half. So I need to derive this so that I can find the rate of change. So what is the derivative? First of all, we get to write dy dx because we're actually using those letters.
1 plus
1.
bracket 2x plus 2b negative 1 bracket 2.
Good. Why are the brackets 2? Chain rule, derivative of the brackets. So now I've got 1 plus this 2.5 cancel out, right? Because they become 1. So then I've got 2x plus 3 to the power of negative half. And I'm going to write it up here. 1 plus 1 over 2x plus 3, all square rooted. Okay, so this is the derivative. I want to know what the value of y, or the rate of increase of y when x is 3. So what do you think I'm going to do? I'm going to put 3 inside. Okay. So let's do that. So 1 plus 1 over 2 times 3 plus 3 is 1 plus 1 over what? 3, right? Because 2 times 3 is 6. 6 plus 3 is 9. Square root of 9 is 3. So this is 4/3. Okay, so the thing is, though, this is not our final answer.
Yes. No.
So what I want to do is think about how I can write something a little differently. So I'm going to change. No, that's fine. That bit is what we need. We're just not finished. Because at no point have I used this. Because I'm saying that x has a constant rate of increase of this. This is just my rate of y, okay, for now. So, well, that's not entirely true either. I'm not done yet. Okay, so what I want to do is think about, this is where it gets a little bit hard. I'm going to do another example that I think will make this slightly easier. But I want to figure out what I actually need to do here. I'm actually interested in the rate of the difference of y with respect to time, not with respect to x. I have been told the rate of increase of x. I did not write that bit down, did I? Rate of increase of x is this. I want the rate of increase of y with respect to time. So the way that we always write this is dy times dt. So we always put the thing on top up here and the thing on the bottom over here. And then if we multiply these things, whatever this is and this is, they're going to cancel out, right? So they have to be the same. What is the only other variable I have in this question? I have dx, right? This is my rate of increase, okay? So I have dx dt is this. This is the rate of change of x with respect to time. They gave us that. What we found was the difference of y with respect to x. That's what we just found. So what we need to do now is put those things together. So actually the rate of change of y with respect to time is 4/3, which is what we just found. That was just dy dx. And the rate of change with respect of x to time is 0.06. And then you just type that straight into a calculator and you get 0.08. And that is my actual final answer. I'm going to do another example with a cube. Yeah? Sorry? Time. So what I need to think about is when the question is giving me information, What are they asking about? This question asked me about the change in X and Y over time, right? With respect to time. That is what the question said. So that I kind of didn't write it. But remember, I said that sorry, let me start that sentence again. I said at the start, I didn't write it all down, there is a curve and there is a dot moving along the curve, right? That 0.06 was the rate at which it moves along the X coordinate, right? And that is a steady rate, we're told. And we're asked for the change in Y. But we're asking the change in Y as time goes on at the particular point of X. Because it's a curve, if X is consistent, Y can't be. Otherwise, it would be a straight line, and it's not. Do you get what I mean? Sort of. Let's do another example. Did I save that or not?
Yeah.
I did? Okay, cool.
No, 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 it just. Just in case.
Doesn't matter if we've got two. All right. Okay, let's do one with a cube. All right, so we're going to get my wonderful drawing again. Hey, I haven't even started yet. You can't laugh at it. Actually, not bad. Okay, I'm going to call this X centimeters. I could call it S, but I'm not going to because we're going to use the letter S for seconds. Okay, so what I am told is the side of the cube increases at a rate of 5 centimeters per second. Do you use this notation in physics? Great. So we should be, do you take physics? You should be familiar with it. S with the little -1 means per second. All right. So at 5 centimeters per second, the side of the cube increases at that rate. I want to know the rate of increase of the volume. So find rate of increase of the volume when X is 3. So what I'm going to do first is write the thing that I'm trying to find. I want to know the rate that the volume is changing with respect to time. As time moves on, what is the rate that the volume is growing in or increasing? So again, I'm going to have dV over here and I'm going to have dt over here. What is my only other variable? Dx, right? So this is going to be dx, this is going to be dx. What do I know? What is this information here? I'm going to highlight it. What is this information? That is how much X increases by over time. So what part of the equation is that? It's this bit, right? It's telling us. So all we need to do is find dV dx. Do we know anything about the volume? It's a cube, right? So the volume equals X cubed because it's a cube. So then this is just, sorry, 2x, 3x squared. I've derived the volume to get dV dx. So now I can just put this together. 3x squared times 5. What is X? 3. I want to know when X is 3. So I've got 3 times 3 squared times 5. And if you put that all together, you get 135 centimeters. Now, it's really important. You can lose marks on your exam for not using the right units of measurement. What do I put here? You missed something before that. Cubed. This is a volume. I need to write cubed, then per second. All right, so be really careful. If it's surface area, it's squared. If it's length, it's just normal. If it's volume, it's cubed. Be really careful about that.